Hello, dear learners. Welcome back to the Lesson BCE YouTube channel. Imagine this. If you're traveling right at the speed of light and you look into a mirror, do you actually see your reflection? It's kind of a mind-bending question, right? Well, this exact puzzle plagued a young Albert Einstein as he imagined riding alongside a beam of light. Today, we're looking at Einstein's ideas, focusing specifically on basic relativity. I am incredibly excited to guide you through this explainer because we're about to explore some of the most reality-shifting physics ever discovered. As we'll see, space and time are not absolute. Oh, and before we jump in, please don't forget to subscribe and like our channel. Okay, let's dive into our lesson objectives for today. We're going to understand the basic ideas of Albert Einstein and relativity, learn exactly why the speed of light is so special, solve some simple relativity equations for time dilation and length contraction, and figure out the true meaning of E equals mc squared. Kicking things off with Section 1, the genius of relativity, and Albert Einstein's massive 1905 breakthrough. So, in 1905, Einstein introduced the theory of special relativity. Now, he couldn't exactly build a spaceship to test these concepts out, so he relied on thought experiments. For centuries, classical physics taught us that space and time were rigid, completely absolute. But Einstein's grand realization completely shattered that assumption. He proposed that, actually, only the speed of light is absolute. To build his theory, he established two really important ideas. The first one is that the laws of physics are the exact same in all inertial frames. Basically, if you're moving smoothly at a constant speed with no accelerating, the physical laws governing you are exactly the same as if you were standing perfectly still. Moving right along to Section 2, the absolute speed of light, a universal constant. This brings us to Einstein's second big idea. The speed of light in a vacuum is 300 million meters per second. That's our constant, c. It is so unfathomably fast that we just never notice the effects of relativity in our slow, everyday lives here on Earth. But here is the ultimate cosmic speed limit. Literally no object can move faster than light. And what's really wild is that even if observers are moving in completely different directions or at totally different speeds, they will all measure the exact same speed of light. Because light refuses to change, space and time themselves have to bend and adapt to make the math work. Let's look at exactly how they adapt in Section 3, time dilation, and bending time. Einstein discovered that time literally slows down for objects moving at very high speeds. Faster motion equals slower time. Imagine you're standing on a platform, and a train zips past you moving near the speed of light. If you could somehow peer into the window, a clock on that train would appear to be ticking much slower than the watch on your own wrist. We can actually calculate this using a simple equation. Don't let the variables overwhelm you. It's all about perspective. The time measured by a stationary observer, t, is calculated using the proper time inside the moving frame, t sub 0, divided by a factor of their velocity compared to the speed of light. Let's look at a solved example to see this in action. A spaceship is moving at a very high speed. An astronaut measures exactly 2 seconds passing inside her ship, but a stationary observer back on Earth measures 4 seconds. This perfectly illustrates time dilation. Time actually passed more slowly inside the moving spaceship. Now, if time can stretch, it only makes logical sense that physical space must shrink. Welcome to Section 4, length contraction. Objects moving near the speed of light actually appear shorter in the direction of their motion. Higher speed means a shorter observed length. Now, it's highly important to note that the object doesn't feel squished to the people inside it. Their original length remains totally normal to them. It only shrinks from the perspective of an outside observer. Looking at the math, we see a really similar structure to time dilation. The contracted length seen by the stationary frame, L, is equal to the original length, L sub 0, multiplied by a factor of their speed. Once again, velocity and that universal speed of light totally dictate how much physical space bends. To put that into perspective, imagine an Earth observer watches a spaceship fly past at 80% the speed of light. If that Earth observer measures the ship to be 40 meters long, the passengers inside would measure that exact same ship to be significantly longer. Everyday absolute measurements just fly out the window when we approach the speed of light. All right, bringing us to our final section, Section 5, mass-energy equivalence. Here we encounter the most famous equation in all of physics. Einstein introduced E equals mc squared. Energy equals mass multiplied by the speed of light squared. The crucial point here is that this elegant equation profoundly unifies mass and energy. Small amounts of mass can produce enormous energy. They are quite literally two sides of the same coin. Think about an atomic nucleus. Because c is the speed of light, that massive 300 million meters per second number, and because we're squaring it, it acts as a colossal multiplier. That means even a tiny, almost invisible speck of mass locked inside atomic nuclei holds an absolutely enormous amount of energy. And this isn't just a fun theory. We see this principle in action all around us. It's used in nuclear power plants, it's what drives the sun's energy through fusion, and it's the core of all nuclear reactions. So what is our final concept? Einstein showed us that space and time depend on motion. Time is not absolute, length is not absolute, and mass and energy are deeply connected. These ideas completely changed modern physics. Before we go, here is a practice problem for you to try out. Find the energy produced by 0.001 kilograms of mass. Use E equals m squared and comment your answer down below. That's all for today's explainer. Keep learning and exploring physics, and don't forget to subscribe and like our channel for more lessons.